Today, I'll defend my thesis on sim-to-real reinforcement learning for dexterous and collaborative manipulation. And let me start by introducing the modern robot learning stack. I think it's surprisingly simple. Instead of hand engineering policies, what we want to do is we want to learn from data itself. And increasingly, we are interested in questions regarding the sources of data to train a robot. So let's talk about that. Nowadays, teleoperation seems to be the dominant approach. And over the last few years, we have seen an explosion of easy to use interfaces that allow us to control robots and do more and more dexterous things. And I think the Aloha system at RSS 2023 was really the one that made the community believe this approach can scale. Look at the dexterity you can achieve with just a low-cost bimanual robot system, doing really dexterous things like in-hand rotations and um solving assembly tasks, solving these NIST assembly boards, all of which people thought really parallel geographers cannot handle, but it seems like this was very promising. And along with Google, the team, Aloha team, next worked on creating the system called Aloha Unleashed at Coral 2025. And they wanted to scale up the number of demonstrations provided for these tough tasks. Here it's the shirt folding task. And they increased the data from 2,000 to 8,000. But I really think the story starts showing a crack now. Collecting more and more demos started to hit a plateau. Even when we went from 6,000 to 8,000 demonstrations, the success rate was still 75%, and we couldn't go beyond that. Apart from that, there's a second problem, the speed. During teleoperation, the robot moves slowly, carefully, well below the limits of the hardware itself. So I think we are really restricting the robot's capability. That's my first claim. Teleoperation limits the robot's capability. Uh, Here's a video 1x of my collaborator Max trying to open a bottle with teleop. This is a very simple daily task. Normally takes a human a couple of seconds. But in this leader-follower setup, navigating the robot's kinematics and the gap in perception makes the task much longer. And this problem is more pronounced for complex robot embodiments like dexterous hands, where the control problem requires precise and forceful contacts. Teleop restricts robot hands to largely pick-and-place tasks. If this green circle is everything the hardware is physically capable of, teleoperation only ever captures a tiny speck in the circle. Now back to the robot learning stack, imitation learning takes teleop data, which is state action pairs, fits a neural network policy. But two problems with this story. First, as we just saw, teleoperation caps the quality of this data below the hardware limits. And second, this data is static and offline. It's almost entirely successful trajectories. There's no demonstrations of how to recover when things will inevitably go wrong. To see what we are missing, watch a human do dexterous work, 1x speed. This video is almost too fast to follow and understand what's happening. So in order to really grasp what happened here, let's try to slow it down. And what we'll notice is that the human dexterity here is full of recovery motions. For example, this video starts with the human picking up the wrench. It notices it's not quite the right orientation, so it rotates its hand. Then it notices it's not right side up. So again, it has to do a recovery. Then it starts screwing this nail, notices the nail is not properly aligned. So again, adjust it with his finger. And this is finally when it's got the system in a stable state and can do the rest of the screwing. Similarly, human collaboration is super fast and reactive. Here is a clip from Ego 4D, where two humans are collaborating in a kitchen together. During collaboration, you constantly read your partner, adjust your motion, while executing a number of different manipulations yourself. And this kind of motion, while super intuitive for humans, any human in a kitchen would be capable of these kind of motions, it's very difficult to collect with Teleo. So how do we achieve robots that can do these kind of tasks? I think we should let robots learn from their own experience. In this paradigm, the policy generates its own data by doing trial and error. And I think in order for this trial and error, which is going to be low-level joint actions, to be safe, we'll do this inside a simulation, which is an approximate model of the world. And now the learning stack looks a bit different. It's kind of the same arrows and the same learning from data story, but there's a reward attached to the data state action pairs in our data set, and it contains information about failures, counterfactuals, and this process of trial and error really lets the policy learn to recover. This paradigm is called sim-to-real reinforcement learning. In locomotion, this process of sim-to-real RL has been really successful, unlocking the limits of robot hardware. For example, the Cassie broke the Guinness World Record for the 100-meter dash under 25 seconds with this process, sim-to-real RL. Story is similar for things like quadrupeds. Here's the MIT Mini Cheetah learning a record-breaking sprint, moving super fast, almost 4 meters per second. And last, there's this Swift drone racing system. It was the first autonomous system to beat human champion pilots, kind of like teleoperation. Um, and it's able to do these superhuman turns, very tight turns, which is just beyond human capabilities. So here's the question that drives my entire thesis. If this is working so well in locomotion, what is holding it back in manipulation? And I will talk about 3 ways in which this sim-to-real RL pipeline is harder in manipulation than locomotion. The first challenge is capturing real-world diversity. If you look at locomotion again, the robot is really making one external contact with the environment. For leg-width locomotion, from the videos before, this contact is encircled here. It's just the large static ground. It never moves. And for agile flight, the contact is being made by air resistance. And again, it's a kind of a bounded nature of contact, so it's easier to model. On the other hand, manipulation looks so different. Was this assembly line worker? Um, Beyond the super fast speed, her hands are making contact and manipulating multiple object geometries with different physical properties. The manipulated object in itself is making contact with other objects in the environment. And contacts extend to other humans who are dynamic, moving, not static. So that's challenge 1. Challenge 2 has to deal with RL itself and the exploration challenge, getting reward signal to learn from. And even here, locomotion kind of has it easy. With a single move forward progress reward, DeepMind showed back in 2017 in Mojoko, you can train these diverse robot embodiments to run, jump, crouch, climb through these mazes. And I think it's really because throughout the state space, the reward is dense, which makes RL exploration easier, as there's always some reward gradient to follow and make policy improvements. On the other hand, it's more difficult to write reward functions in manipulation tasks. Consider things like kneading dough. It's not super clear what's a dense reward here, what's the sequence of states the robot needs to complete. I think the signal lies in the narrow corridor to the goal. If you're not in this path, you're basically not getting any signal for policy improvement. And this makes RL exploration brutally hard. So that's challenge 2. And challenge 3 is about closing the sim-to-real gap itself. That is training RL policies in simulation that will actually transfer to the real world. And even here, if we compare locomotion with manipulation, on the perception side, I think proprioception alone gets you a long way in locomotion, which has almost no sim-to-real gap. But manipulation really depends on tactile visual perception. both of which have been more difficult to model in simulation and have higher gap. Even in terms of dynamics, like I mentioned earlier, the external contact is just with a single heavy body. This is the ground. So when you do sim to real transfer, it's more forgiving because the ground will never move. Whereas manipulation will contact these light, dynamic, moving bodies, which are far harder to simulate faithfully, also has higher sim to real gap. So the gap is wider on both axes. So these are the three challenges my thesis tackles: capturing real-world diversity, guiding RL exploration, and closing the sim to real gap. We will keep coming back to this roadmap, but let's start with the first challenge, capturing real-world diversity. And let me start by saying the progress of sim to real RL, even in dexterity and manipulation, has been great, producing very cool videos. For example, the seminal work on in-hand block rotation by OpenAI, and then solving a Rubik's Cube one-handed, which I think is a task even difficult for human beings. And then these results are not exclusive to OpenAI. Academia also reproduce these results, doing even more challenging tasks like top-down in-hand reorientation, where you're controlling the object against gravity. So the common problem here, though, is that each of these projects are single task. And there's a considerable amount of task-specific reward tuning and environment design that has to go in to make these policies work. And for one task, you're like spending multiple months to get this pipeline up and running. Said differently, each project hand-engineered this tiny overlap between what the robot can do in the real world and what the robot can do in simulation. And if you have to do this manually every time you have to set up a new task, this won't scale. Consequently, prior work learns one policy per skill, a separate policy for in-hand rotation, separate policy for spinning, another for tool use, each with its own task specification, reward, and environment design. This doesn't scale. We don't want this zoo of brittle single skill policies. Ideally, we want this unified multitask policy. And we want to train this with a single unified objective that produces general dexterity. That's the goal of the first piece of work I'm going to talk about. Train an RL policy in simulation that can apply zero shot on novel tools and tasks. This is SimTool Real, joint work led with Tyler, which will appear at RSS this year. And the key insight here is to unify manipulation as goal reaching. Instead of thinking of specific verbs like hammering or sweeping, what if we consider each task to be a composition of sub-goal reaching problems? So here, the green whiz that you see is showing the goal poses that the policy is tracking. And we can break down large amount of manipulation problems by just composing multiple goal reaching problems. And that makes the training objective for RL simple and general. We will just get good at this unified training objective where we'll procedurally generate primitive objects in simulation, sample random goal poses for the robot policy to track, and then train with massively parallel RL in simulation, manipulating these random objects to random goals. And if we keep getting good at this singular objective, we can zero-shot transfer at test time to new tools and new tasks. We don't require any task labels, no power task rewards, just this unified objective. And the policy design itself is object-centric, so let's be concrete. The input is proprioception, a current object pose and a grasp bounding box of the handle, the goal pose, and each of this is going into an LSTM, which outputs joint position targets for both the hand and the arm. And this singular policy, which was trained to go to random goal poses, can now at inference be prompted by a human video, for example, to reach these goal poses that complete actual tasks we care about. So here we collected a human video who is showing us how to sweep a brush across the table. And from this, we extract a sequence of object goal poses. And the sequence of object goal poses is tracked one by one by the object-centered policy. Each time it hits a goal, we provide the next one, and we can complete the task by composition. And we evaluated this policy zero shot across 6 tool types, 12 objects, 24 tasks. And a single policy was good enough to get reasonable success over this entire variety. But it's not the breadth that I think was hard. I want to emphasize the hard part of these tasks. First, this is high dimensional control. We are controlling 22 dots on the hand, 7 dots on the arm. Second, every task requires multiple contact switches. Grasp the tool, reorient it in hand, and then use it. And for me, the most important part is how fast it is. This is 1x, 60 hertz control. These are fast fluid dexterities that teleoperation simply cannot connect. So the next question I want to ask is whether the training objective was the one driving the generalization. Remember, we trained on these primitive objects with random goal poses. And at test time, we were working with tool meshes with human demonstration goals. And we saw a very clean trend. As we scaled reinforcement learning in simulation to 120 billion environment steps, we saw training reward to climb steadily. And consequently, correlated with it was the zero-shot task progress on real tool meshes. So it does validate our hypothesis that as long as we get good at goalpost reaching, we can do a lot of useful things in the real world. And let's compare with some baselines to set a comparison point. Our method SimToolReal is able to do both grasping of objects and then the in-hand tool rotation, which is important. A common baseline in prior works is actually using fixed grasps. We'll do the grasping, then we'll lock the grasp. The arm will try to complete the rest of the tool rotation, but this can lead to collisions with the table, and it's not a general solution. Kinematic retargeting from human hand motion is another option, but human videos do not contain any contact forces information, which makes it harder to complete like thin handle grasping. Finally, SimToolReal is not perfect. There are failures. For example, things like dropping objects after grasping or getting stuck in between rotation and not being able to achieve goals, or even failed grasps. But notice how it chases after the object. And that's what RL gets you. RL enables the policy to recover. Here's a video where the policy actually did succeed after failure. The policy goes in for the hammer, drops it, then can go in again, reorient it at hand, get it stable, and finish the task. So stepping back, the story of SimToolReal previously was a lot of task-specific engineering for each thing we want to do in the real world. Our contribution to challenge one is to make the sim RL objective general and unified, goal reaching on random objects. So single policy itself covers the large variety and diversity of things we want in the real world. So that's how we capture diversity by a unified objective for dexterous manipulation. Next, we want to move on to harder manipulation tasks, which will make the RL exploration more challenging. Specifically, consider contact-rich, precise assembly tasks. These are forceful, millimeter precise skills that are very difficult for robots. There's a question.
Yeah, Kushal, it's me. Just a quick clarification question. In the previous paper, can you talk a little bit about how you were tracking the objects in real time, at inference time rather.
We are using an off-the-shelf tool called Foundation Pose, which is a 6D pose tracker, and we run it at 30 hertz.
Okay.
Okay. So coming back to our next goal, this is contact-rich precise assembly. These are tasks like tight peg and hole insertions. See how the robot is kind of using the contact to feel for the hole region and then goes in. Second, assembling a multi-part beam structure where the assembly parts start scattered on the table. And last, consider screwing a leg onto a tabletop base. These tasks are not just about being precise. It requires reasoning about contacts. And what makes this problem especially hard is that the initial states of the objects are all over the place, and the problem is defined just by the goal state to achieve. So going from start to finish is not a single motion. It's a long chain of exploration of things like grasping, in-hand rotation, goalpost reaching, and the final contact-rich interaction with the fixture. Success signal is only achieved after this long horizon of exploration, which can make RL hard. One option that's kind of obvious here is why not just use reuse simtool real and see what happens. It's already a goalpost reaching policy. So what we can do is we can detect the current object pose. We can detect the goal object pose, which is the fixture pose, and just ask the simtool real policy to track this. And this kind of doesn't work for tight insertions, and it's quite unsafe. Here we define clearance as the distance between the peg and the hole walls, kind of visualized here. We'll start with a simpler version of this problem. SimTool Real was trained to reach goals in free space. So even a small imprecision makes the peg contact with the hole fixture. And now it's not going to be responsive. It's going to try to ignore the contact forces and just try to bulldoze in. And at 2 millimeters clearance, this is more hard. And this generally was forcefully, this policy is generally forcefully ignoring contact, which kind of makes this unsafe for deployment. So this was kind of a bad idea. So let's try option 2. Just train RL from scratch on this new task. We assume access to the CAD assembly, CAD design file, which defines the goal state for the assembly. And we can spin up parallel simulation environments with randomized initial part positions and try to solve this with RL. We can also follow prior work on assembly by disassembly to decompose this multi-part problem into subtasks, the part 1, part 2, and also some intermediate goal poses. What we do is basically pull apart the structure in sim from the final position, and basically disassembly, which gives us the reverse sequence of intermediate goal poses, which our RL policy can track. Still, even with this sequence of goals, it is a sparse reward, and success stays at 0 even after 24 hours of training. We also tried our best to do dense reward shaping, adding some terms to make the contact interaction more easy for the robot, but we couldn't get it to work within 24 hours of training. So let's diagnose why each option failed side by side. Option 1 had a great prior, but the wrong one. It only wants to do free space goals and bulldozes whenever it sees contact. RL from scratch has the right RL environment setup, but it has to explore the entire long horizon task from scratch. So the idea kind of speaks for itself at this point. We want to pre-train the policy on free space goals on random objects before specializing and RL fine-tuning on these contact-rich tasks. This is Play to Perfect, again, work led by Tyler, with Tyler, and this is currently in submission. The key idea in one line: learn to play in free space before perfecting contact-rich assembly tasks. Stage one is the play pre-training. The policy practices random goal poses in free space, just like SimTool Real. It's a task agnostic prior defined by free space goals, and it can be shared for multiple new assembly tasks. The second stage is perfection. We take the play prior, RL fine tune it on the actual contact rich assembly task. Now the goals are in contact, and we can use the same player again and again for different assemblies without modification. And finally, we transfer this system onto the real robot. So here are the three tasks from before where RL from scratch wasn't working at all. And with pre-training, we can quickly solve these tasks, not just taking 24 hours, but we can get near 100% success rate within 5 hours of training for all these tasks. Also, coming back to those precise insertions that the free space policy couldn't tackle, we'll do the tight clearance of 2 millimeter first. And what's interesting to see is the policy is not just precise. It's a kind of feeling for contact and trying to slide the peg in rather than just being slow and precise. And with a 0.5 millimeter clearance, here's the robot execution again. We did a systematic analysis in simulation comparing the free space policy with play to perfect with tighter and tighter hole clearances. Our policy play to perfect is robust even for very tight clearances like 0.2 mm. But the sim to real policy kind of just works when the goal is basically free space. The question we really wanted to answer in this work is what makes a play prior good. Specifically, we ablated 4 factors: object diversity, training objective, trajectory diversity, and goal imprecision. And we checked how it affects the RL fine-tuning stage. What is the sample efficiency with different design choices? First, we noticed that object diversity matters. More objects during pre-training leads to a higher ceiling during fine-tuning. So the blue line is trained on 1,000 objects, and the other 2 lines are trained on less objects during pre-training. Second, the training objective must emphasize both translations and rotation, so 6D pose goals. If you just do translation, you barely get non-zero success rate. If you just do rotations, it's good, but you're still sacrificing the ceiling of performance. Next, trajectory diversity matters. We train with random goals, but you can imagine also training with fixed trajectories, which doesn't work as well. And last, we are tackling precise contact-rich tasks. So during free space goal reaching, we need the precision during this goal reaching to be precise. And if you're not precise, the performance is worse during fine-tuning. But the overarching theme behind all these design decisions is that every design choice that we end up using in Play to Perfect is the one that forces the policy to learn in-hand manipulation. This is useful because it teaches the robot to use its fingers, uh, precisely control the pose of the object, and do the contact-rich task of assembly. Let me close Play to Perfect on real hardware is stress tested with diverse initial conditions. Here are some videos. Objects are scattered over the table with different initial poses. And you can notice that some rollouts take more time than others. And that's because there's some failures happening, and then the policy recovers from those failures. This is a story of reinforcement learning again. If we train with RL, we'll get this ability to recover from failures. Let me highlight a couple of examples. And these failures sometimes happen at the ultimate last step, and then the policy can recover. Here's another example where the insertion fails at the last possible second, but the policy goes in and tries again. So That closes the second part of this talk, guiding exploration, which is addressed by bootstrapping reinforcement learning with a play prior to guide exploration. Now we'll talk about the last challenge. And this challenge has been existing in both the works I have shown before, which is the sim to real gap. Everything so far was deployed zero shot, train in sim, run in real, hope it transfers. But there's always a residual gap. For example, sim to real, we saw the failure examples. It would pick up objects, drop it. Even play to perfect would sometimes collide with everything, create havoc. This was not happening in simulation though. Quantitatively, sim to real dropped by 12 percentage points, play to perfect dropped by 20 percentage points. So we are always having this residual gap. But the deeper point is that so far when we did sim to real, we had a static policy. This policy was never closing the gap after deployment. So it can't use real experience to improve. And we'll always have to accept this residual gap. That's the question I wanted to ask next. Can we improve a sim trained policy after deployment using real robots itself? We tried this idea with XM, led with Prithvish at Coral 2025. As a first step of this approach, we took a human video demonstrating a task like placing the mug. And we tried our best to create the best possible photorealistic simulation from it, using 3D computer vision tools and even track the object motion. So this is simulation, and you can see the images look quite photorealistic. Once we have this photorealistic simulation with the object motion encoded in it, we can define a reward function and do reinforcement learning. These policies are often trained with privileged state, so we need to actually transfer it back into the real world. We have this photorealistic simulation, so let's just do teacher-student distillation and get an image-based policy out. And with this photorealistic simulation view, you would hope that the zero-shot transfer just works. And it does work for the easy tasks. For example, this is pick and place. Both sim and real success rate is basically 100%. There doesn't seem to be any gap between sim and real. But more challenging tasks, they reveal a large gap between sim and real performance. For example, in sim, the robot can always go in and put the mug into the rack. But in the real world, there's some slight imprecisions during the grasp and then during the insertion. And it's almost not perceptible here, but the robot misses the rack by an inch, which is not a success. What's happening here? We wanted to investigate this mismatch more deeply. So what we did was we replayed the same actions across both simulation and real. And what's happening here is everything is same, the robot joint state, the object motion. But what's not same is the image embeddings produced by the policy's visual encoder. Here's a TSNE plot visualizing the feature space, and you can see there's a difference between real and sim. Now, it would be really ideal if we had some mechanism of minimizing the distance between these image embeddings, and then there would be no sim to real gap. And that's what we did by proposing an online calibration scheme to reduce sim to real gap from real world experience. Concretely, we rolled out our image-based policy in the real world, and the actions that were executed in the real world are replayed in this digital twin spawned with matching initial state. Then we have natural pairing between a sim rollout and a real world rollout. We can compare the image embeddings. Now, there can be some slight dynamic gap mismatches. So we won't do explicit time step matching, but rather use a contrastive loss, which is going to put nearby time steps close with each other and far away time steps further away from each other. So before alignment, the image embeddings used to look very different in feature space. And after this alignment, image embeddings corresponding to the same environment states are now much closer, as shown in the updated feature space plot. Minimizing the visual center-real gap also helps improve the performance of this policy. Earlier, it would miss the rack more frequently, and after 10 rollouts of calibration, we can see a significant increase in task success. Um, so this was the hardest task, the mug insertion. In easier tasks, we actually don't even need calibration because the sim-to-real gap is not even there. The zero-shot performance is good enough. But as we increase the hardness of the task, this alignment process is needed more and more. Here we just did the alignment with 10 rollouts, but it would be an interesting future experiment to scale more and more real-world experience and see if the performance keeps improving. So that's challenge 3, closing the sim-to-real gap by online alignment of the visual encoder. Before I conclude, during my PhD, I worked on other projects towards the broader goal of dexterous and collaborative manipulation towards robots that are doing hard manipulation tasks. Um, I want to talk about that next. Starting with diversity, I talked about dexterous manipulation. There's a parallel collaborative manipulation story as well. Capturing real-world diversity in collaborative manipulation means capturing people, and that requires models of human motion. Without it, a robot is unresponsive in a shared space, and it can be generally discomforting in such a setting. The human is planning around the robot rather than any semblance of collaboration. But if we can have predictive models of human motion, the robot can be more smart, anticipate the person, and make room preemptively. This is a line of work across 3 papers on modeling human motion for collaboration. To enable all this research, we first went in, collected COMAD, a collaborative manipulation dataset. This is a high quality motion capture data of 2 humans interacting with each other and also some human robot interactions. Using this data, we developed models of human motion forecasting that enable the robot to plan around human motion. Here's me stress testing the system by going in repeatedly, and you can see the robot always being able to react in advance. Whenever the motion forecasts touch the pod's safety region, the robot stops stirring. Even for the second challenge, which is guiding RL exploration, we can do things beyond just pre-training. There's another source of prior that I've worked on, which is human videos. Specifically, I want to highlight this work, one-shot imitation under mismatch execution, where the human and robot motion for the same task kind of differed. Still, we were able to learn this mapping between the human video into robot actions. Lastly, we talked about handling the sim-to-real gap online by real-world experience, but we can also approach this problem offline. The specific construction we can do is consider a problem of offline learning from mismatched data. So our data is not something that can directly work. So the sim-to-real gap. And this kind of gap also exists in human to robot transfer. So we had this work in ICRA last year called X diffusion, which treats the embodiment gap between humans and robots as noise and co-trains on it smartly in the diffusion process. I also had earlier work on planning with imperfect human models. Here is an example of multi-agent navigation, even when the robot has imperfect models of the other agents. Put together, this fills out the thesis grid. I think these are the 3 key challenges which are restricting sim-to-real RL in manipulation. And I think we have made progress in enabling manipulation robots to do more hard tasks. Let me close by zooming all the way out and talk about the broader goal of physical AI. I think there's a general trend that we want robots that demand less from humans. And classical robots demand a lot. They demand you to code up hand engineered control policies. for each task the industrial robot will work on. And anytime the environment changes, object changes, the human has to go in again and write the control policy. The shift has been towards these robots that learn from data alone. It requires less manual engineering. And even within this learning-based robots, I think there has been a trend of demanding less and less from humans. For example, imitation learning from teleoperation asks a lot from the human. It asks the human for both halves of the manipulation behavior, setting up this task environment, and also the control to solve the um, task. And this method is not great for high dimensional control because of this leader-follower setup. And in some senses, there's a subhuman performance ceiling. The speed and the dexterity is not comparable to a human, even if the hardware allows it. Now, sim to real RL asks for less. The human provides only the tasks in simulation, and the robot self-learns the control through trial and error. Now, high dimensional control is more feasible because the robot will discover it via its own. And the performance can be superhuman because it's not bounded by what a person can demonstrate. And the last horizon, which I'm particularly excited about, is curious robots. And the most curious robots that we see in the real world are babies. Here is a baby playing in a playroom. Nobody hands them a task list. They are just curious about different toys in their room. They play with it, get good at playing with them, and move on to the next thing. And I think this is also a path for a curious robot who chooses its own tasks that interest it, then solves those tasks, and then chooses its next task. This requires no human to be in the loop. Concretely, here's the loop I want to build towards the vision of continual learning robots. The policy acts in the real world, collects real world rollouts, introspects on what happened. Where did I succeed? Where did I fail? And from this introspection, we can update our internal model of the world, update the things we want to practice on in simulation, build kind of like our workbook. In this simulation, we will do trial and error, uh, generate data for RL updates, which goes in back to the policy. So this is a continual learning loop with rollouts, introspection, simulation update, practice, improvement. And just like humans, I imagine that the process starts with some human supervision at the start, but increasingly the human goes out of the loop. And that's where I see this work heading. With that, I want to say none of this work in this thesis was solo and couldn't have been done without the help of so many people. And I want to thank everyone. Um, Tapo, thanks for always pushing me to put my robots closer to humans and to tackle the genuinely hard problems in robotics. Kwan, for bringing so much life into the Cornell robot learning community after you joined and supporting me throughout. Um, Karen, thank you for being so kind and a positive influence of me. I always remember you saying, reflecting on our time together, saying it's not the results that motivate you, it's the process of how we got to the results, which has always stayed with me. Um, Thank you, Jeanette, for making me feel like a native part of the IPL lab. Um, Not just research, you made me participate in things beyond research, which really made me feel at home in your lab. Um, Vichu, thanks for introducing me to all the things computer vision is capable of. As a roboticist, I always thought nothing in CV actually works in the real world, but somehow Vichu's things always did. So beyond that, I think Vichu is not just a computer vision guy. He has so many ideas in robotics. Meetings with him are usually me listening to his ideas rather than me pitching my own ideas. Last, my advisor, Sanjavan. If I look back to the start of my PhD, I really think I did not know how to think. Sanjavan taught me how to think clearly and from first principles. To this day, when I'm stuck in a hard problem, I still ask myself, what would Sanjavan do in this situation? So yeah, through this PhD, I took away one valuable thing, which is how to think. And honestly, that's like makes the entire experience worth it. Finally, this thesis would truly not exist without Prithvish. He was a co-author on all the papers in the first years or 3 years of my PhD. After my third year, I started to doubt if I can ever write a paper without Prithvish. So yeah, it's been an incredible journey. We defined a lot of our research agenda together through conversations and just debating whether this research even makes sense. So I really enjoyed all those conversations. Um, I did write some more papers after Prithvish. That was due to Tyler, with whom I think I worked on some of the coolest robot experiments of my PhD, none of which I think could have been done alone. Finally, I want to thank all my lab mates from different labs at Cornell and Stanford who have supported me on this PhD journey. There's just so many people I want to acknowledge individually, but um, um, it's just so many to say this in this bounded time. Thank you all. With that, I'm going to let the robot speak for itself, draw a smiley, and we can take some questions from the audience.
Awesome. Thanks for that wonderful talk, Kushal. So now we have time for audience to ask questions.
Hi, Kushal.
Hi.
Yeah, very cool. Yeah, I really enjoyed watching the real robot videos. I have a question for the Exim work. So in that paper, uh, you talk about how you can bridge the visual domain gap between sim and real. I was curious if you also have any insights into, how to bridge the dynamics gap, which you mentioned.
Yeah. Um, so we tackled specifically the visual gap in XSIM, and we did this through a process of real to sim after deployment. So what we did was we did some real rollouts, reflected on the visual embeddings, and then updated the simulator. I think we can do a similar story for dynamics too. And I think we have seen papers in the locomotion domain that have done similar things. What makes manipulation different, I think, is the perception side. So that's what we focus first, but definitely something we should focus on in future work.
Yeah, cool. Thank you.
Well, I have a question. Yeah, great presentation. Um, question I have, you talk about RL a lot in this work. Do
Hmm.
you see, I can imagine like the simulation RL is a bit like RL, like with verifiable reward, kind of. Do you think there's any way that there'd be like an RLHF for these kind of robots?
Yeah, I think the RLHF is basically the process of taking human feedback and then updating policy. I think that's how robots will interact in the real world. They will make mistakes. They'll be dumb. They'll just be like babies. So we need to be good parents and give them feedback and definitely learn from that. I think the scale of RL in the real world and in simulation, they have to be different. In simulation, you can explore low-level joint torques, motor torques. I don't expect that kind of RL to happen in the real world, but maybe at a more high level.
Thanks.
More questions?
Can I ask one? The Sim to Rule like project like it's really cool. Like I've shown this to basically I think at least four of my students and asked them to, brainstorm like similar or like even cooler tasks. One question I have is like so which parts of the methods you think is like kind of can be broadly applied to just like that broader like textual manipulation tasks?
Yeah.
And or which part like actually rely on assumptions on, for example, the primitives like geometric primitives of tool objects or just like tool use tasks specifically? Like what kind of like limitation do you see like for applying this to broader tasks, like maybe deformable manipulation or other kinds of dexterous manipulation tasks?
Yeah. That's a very good question. And for me, I think the broad message of the work is that we need to do some pre-training for dexterous hands before we go on to more complicated tasks. Of course, we did things with the stool primitives and rigid objects, but we need to start somewhere and create priors to do then for fine-tuning on top of it. So we showed one example of doing assembly tasks, but I think more future directions should look at how do we take this prior and then retarget human videos or do articulated manipulation, deformable manipulation. I think starting from scratch is a thing that worked in locomotion. I don't think it will work in manipulation. We need good priors. And starting from this dexterous prior, I think makes sense to me. Yeah, that's I think the limitation.
Maybe I can ask a quick follow-up question from Guan. Did you so you mentioned you use foundation pose for tracking these objects. Did you kind of try distilling that into, your visual policies and seeing how that goes?
Um, we have briefly tried some experiments like that. We found foundation pose to be pretty good for some of the tasks we have already done. Um, I think it starts to fail for small objects. And I think if our teacher doesn't work, which is foundation pose, it won't work even if we do distillation. I think for small objects, we need to rely more on tactile perception, which I'm interested to try out in future work. But for these big objects, I think foundation pose was reasonably reliable. So it wasn't the point that we were explicitly trying to make, but I think it's good. It's a good direction to focus on in the future.
I also have a few questions along this thing. So first question, I guess, is why foundation pose? Why not use, for instance, key points or other things? Because I thought if it's foundation pose, then you need to figure out what is the canonical pose and these things. Wouldn't that cause some troubles? Or yeah.
Yeah, that's a very good question, and I think that's the choice of interface to go from sim to real. I like pose because it's very interpretable. It allowed us to do a lot of targeted testing between sim and real, but there have been concrete works even in the last 3 or 4 months that have used point tracks as the unifying interface between sim and real. One example is this Dex 4D work. Um, I think it's an obvious next step, and if you want to do things like articulations, you cannot be restricted to these pose goals. So if you want to do things like articulations, deformals, we have to move beyond poses and go into these kind of things. Yeah.
I see. So I have another follow-up question. So I guess you're trying to say you want to match the poses. I guess I'm just very curious, how do you handle tasks where speed or force are important? Because I can imagine if you just match the goal, we're going to hit something, right? If you need to hit it hard, you need to match that, you need to be very far apart and you need to match that pose in a short amount of time. So how do you tackle these things? Or let's say if you're pouring water, and then sometimes when you pour, the mass, the center of mass, these things change. So it seems to me that those intermediate posts are very delicate. You need to handle all these things. How do you handle that during training? And yeah.
So the sim to real pre-training policy does not tackle that. We are trying to do just phase-based
Oh,
manipulation. And
I
the
see.
motion between the goals can be suboptimal, like you said. So even if you see some of our videos, it can seem to be like shaking a bit between goals. I think these kind of smoother motions have to be tackled in fine-tuning stage, which was like the precise assembly work follow-up, which will reason more about
Oh,
forces and contacts.
and so the video where you show it hit things is actually already fine-tuned because it looks very smooth.
It's just the pre-trained policy. We
Oh, okay.
just provide the
Okay.
goals. Yeah, I think the policy
Okay.
says it's trained with some external force perturbations, so it doesn't totally collapse under external contact. But we didn't have to train it specifically for that.
Okay. Okay. Thank you.
Yeah. There's a question from Jeanette.
Yeah. Hey, everyone. Hi, Kushal. Nice talk. One point on the key points. If you actually try out of the box key points right now on videos that Kushal and Tyler actually used as input for the policy, they are not working very well at all. We actually ran some tests and, they can't deal really with occlusions and especially with long-term occlusions. They're not good at this. They're basically producing garbage. And if you put that into, a policy like that, it's unclear to me how, this policy would be able to make sense of this garbage, quote unquote. Yeah. So there's a lot of work actually to do. I actually agree with the point tracks and the key points. with what Kushal said, but I think there's a lot of work to be done for the vision community if they want to continue working on this and want to go with this to robotics to actually make it work with that kind of with the kind of statistics that you see in a robot manipulation video. Sorry, this was not really a question, but I just wanted to provide this information because we actually tested the current methods and they're not working.
Yeah, thanks for helping me in my defense, Janet.
Any more questions from the audience, from the committee, publicly, before we go to closed doors?
Okay, maybe I'll ask this since every member of the committee asked a public question. Kushal, fantastic talk, as usual. I was wondering, maybe building up on like the previous question on XIM, you focused on visual realism, and then you said dynamic realism is a part of future work. I was wondering, do you have any high-level thoughts on, does the simulator really need to be accurate in terms of visual realism or physical realism to be able to do the task? Or sometimes you can sacrifice on some accuracy as long as you can do the task. What matters for what makes a simulator good?
Yeah, I think that's an excellent question. I think all models are wrong, but some are useful for planning. Like that's the usual saying, right? I don't think that we need very accurate simulations. We need things to be good enough, and there's different categories of good enough. I feel for manipulation, based on my experience over all of my projects, I generally felt that the dynamics gap, at least for the task the manipulation community is choosing right now, it doesn't exist really between sim and real, at least to a level where that's a bottleneck. I generally felt every time the policy was failing, it was due to some perception errors. But as we move to more harder tasks like deformables, we do need good enough simulations, which I don't know if we have right now. But you bring up an excellent point. Things do not have to be perfect. They just need to be good enough for transfer.
I see.
Awesome.
Do you think it's task dependent or I don't know, context dependent?
I think it's a task dependent, right? Like you need more precision for things like the precise assembly tasks. So even the simulations for the precise assembly task run much slower than free space motion. We get like 4x slower speeds in simulation. And for deformables, the simulation is actually slower than the real world. So yeah, that's the trade-off.